So hello everyone and welcome to the live session. I hope you are doing well. So we have started the very important topic of organic chemistry, that is a reaction mechanism, and we have reached to I think lecture number 5th. Actually lecture number 1 was not conducted, so this will be lecture number 5. If you have not gone through the lectures before which we have taken, then please I will strongly suggest you to go through the topics where I have discussed the basics of substitution reaction, how molecular orbital theory works, how it is able to explain the substitution reaction, what is the SN1 reaction, what are the points in which you miss into SN1 reaction, and what type of question CSIR NET can ask from SN1 reaction. We have also discussed that. In today's class, our motto will be to cover SN2 reaction, and if time permits, we will also cover the topics like comparing SN1 and SN2 together. So, good morning and welcome to the live. I hope you people are doing well. So, good morning Cam Pacific, good morning Prajwal, good morning Praful, the rhythm of the heart, good morning Adi, good morning Rinku, Jyoti, Spread Peace, Priyanka. Good morning to each one of you. So we have reached finally lecture number 5th. Actually, the plan was to teach NGP in this lecture, but since we are going with a little slower pace, I don't want to miss any topic. That's why I am covering each and every topic. And now also we have reached, in today's lecture, we have reached till SN2 reaction. So before starting, I will give you a brief introduction about what we have studied, and for the new viewers, this complete lecture series is going to be in English medium only, because there are lots of students from South India also who face Hindi language as a barrier to understand the things. So we have decided that we will complete this lecture series only in English medium. Okay. Good morning Sandhya, good morning Komal. So very good morning to everyone. Let's begin the class. What we have studied till now is mm, in lecture number 2 or 3, I think we have introduced to you what is MOT, how molecular orbital theory can explain a substitution reaction. Always from a substrate side, we have seen that a sigma star orbital, which is the LUMO, is involved, and from the nucleophile side, we have seen that a HOMO, which is a non-bonding orbital, has been involved. Good morning everyone. सर अपडेटेड स्कोर कार्ड कब तक आएगा? मुझे आईआईटी रुड़की के लिए अप्लाई करना है. अपडेटेड स्कोर कार्ड कब तक आएगा? उम्मीद करते हैं जल्दी आ जाएगा वीर सिंह. एग्जैक्ट डेट तो हम नहीं बता पाएंगे अभी. गुड मॉर्निंग अम्रपाली, गुड मॉर्निंग श्रेयसा, गुड मॉर्निंग मैती. So we were discussing about MOT, no? So MOT we have covered. I have shown you how MOT can explain the substitution reaction. Now in any molecular orbital diagram, we see that the gap between HOMO and LUMO should be low in order to have a faster rate of substitution reaction. So those nucleophiles which have their HOMO higher in energy and those substrates which have their LUMO lower in energy are said to be best substrate, best nucleophile and best substrate respectively. So, and the same thing was explained with the help of your same classical theory also, where we saw that if the size of the anion is very big, then the nucleophilicity will be very high, and the same MOT also says that if the HOMO is very high in energy, then the nucleophilicity will be very high. Moving ahead, we have started with the SN1 reaction. This is how its potential energy diagram looks like. We have a two-step mechanism. When we saw the rate, it is only first order with respect to the substrate. It means nucleophile does not play any important role here. One important step which happens here is solvolysis. Whenever a solvent molecule instead of a nucleophile attacks on the carbocationic center, you generate the product, and this step is called as solvolysis. Always remember, lysis means something is breaking. So whenever a bond breaks, then only a solvolysis step is performed. Now, we have written few conclusions with the help of what we have understood, that there is no role of nucleophile in an SN1 reaction. If you increase the concentration of nucleophile, if you increase the strength of a nucleophile, no matters, rate of the reaction is not going to be affected. So, there is no role of a nucleophile in a SN1 reaction. Moving ahead, we see that then what are the factors which are going to contribute towards the rate of SN1 reaction? We found that it is the a first step in which the carbocation is formed. Since the first step is the rate determining step, the stability of carbocation is going to decide how the rate will be affected. And the second factor was the rate of formation of carbocation. How fast a carbocation is formed can also decide the rate of reaction. On the basis of these two factors, questions are asked in your exam. For example, the question can be asked on the basis of stability of carbocation, or the question which we have discussed here was recently asked on 18th of Feb. If you have given UPSC Geoscientist paper, a same concept question was asked there also, and CSIR NET also have asked the same concept in their previous year papers. And the concept they have used is the rate of formation of carbocation. It means how fast a carbocation is formed can also decide the rate, and it completely depends upon the steric hindrance factor. We have discussed this example in the yesterday's lecture also. Good morning everyone. Good morning Diksha, good morning Sahu, Dhaneshwari Sahu, good morning Pooja. Welcome to the live session. So we also talked about the product, that it is racemic mixture, but actually this is a very ideal condition where a complete racemization take place. In actual situation, we have seen a little bit of inversion product dominates in a SN1 reaction. So I have explained you this via an example also. When we performed this product, or we performed this reaction, we saw that we have 47% of retention product and 53% of inversion product. We saw this inversion percentage is little bit higher because of the formation of an ion pair. See, what is an ion pair? When a nucleophile is eliminated, the positive charge formed at the carbon center, and if the leaving group forms an ion pair, like an ionic compound exists Na plus X minus, that's in the similar manner, if they form an ion pair, then one side is blocked so that the nucleophile cannot attack in this p orbital. That's why the product of inversion dominates little bit. If we use polar protic solvents, then of course this X minus will be solvated, this carbocation will be undergoing solvation. So the possibility of attack from both the sides is favorable. So you form the racemic mixture. But inversion product dominates little bit in an SN1 reaction because of the formation of this ion pair. I hope you have got this concept. Moving ahead, we told you that we prefer polar protic solvents in any SN1 reaction. Why? Because they stabilizes the carbocation, they stabilizes the leaving group, so that the leaving group is not able to form an ion pair, it is not able to attack on the carbocationic center. So that's the reason we prefer here polar protic solvents. And we also know that polar protic solvents decreases the nucleophilicity. If you choose a polar protic solvent, it decreases the nucleophilicity. But in SN1 reaction, the nucleophilicity does not affect the rate. So this is also on a plus side of an SN1 reaction, that yes, the nucleophilicity will also be decreased, but it is not going to affect the rate of SN1 reaction. Okay. Now, once we cover the SN2 reaction, then we will compare SN and SN2 reaction. It will give us a better understanding. Effect of leaving group also can affect the rate. If let's suppose you have two leaving groups, one which goes by a faster rate will be having the higher rate of the reaction. This can also be a factor in deciding rate of SN1 reaction. Then always remember, SN1 reaction forms a rearranged product. So it's our responsibility whenever we form a carbocation, if it can undergo ring expansion, we will do that. If it can undergo hydride shift, phenyl shift, methyl shift, then it's our responsibility to do the rearrangement. That's why always the rearranged product is the major product. Moving ahead, now in today's lecture, we have to start with SN2 reaction. Okay. You must have heard about SN2 in your class 12th also. This was introduced in front of you in your school days only. The basic concept remains the same. Some points which are important, which are important looking exams like CSIR NET, I will be telling you that, and we will focus on that portion also. Sir, in the presence of polar protic solvent, racemization take place or not? In presence of polar protic solvent, of course racemization is taking place. In SN1 reaction, we do use polar protic solvent, and that solvent molecule is attacking in the possible p orbitals. That's why racemization of course take place. Okay, or inversion is little. Okay, you want to ask me that? See, if we take polar protic solvent, then also few percentage of inversion product is generally at the higher side. Okay, once you increase the nucleophilicity of the solvent, then there is a possibility that racemization will take place. If the solvent has a little bit higher nucleophilicity, then its tendency to attack at the carbon side, then its tendency, where the figure gone, then the tendency to attack at the carbon side increases. Condition applied, you have a polar protic solvent, and the second condition, the nucleophilicity of the solvent is also high, so that once it performs a solvation, its tendency to attack in both the p orbitals increases. Then only a perfect situation of racemization would occur. Okay, Chem Pacific, I hope I am able to convey your what I am trying to explain is reaching to you. Good morning, Anusha. Good morning. There are two conditions which I have told you in order to have a perfect racemic mixture. So, what about SN2 reaction? We also call this SN2 reaction as a bimolecular nucleophilic substitution reaction. Nucleophilic substitution reaction. Correct. We all have studied that SN2 reaction takes place only a single step. Let's suppose I have a CS3 group here and a halogen here, which is of course our living group. We have only one, we can say a 0 degree center here, and in front of this we have a nucleophile. We all have studied that in a SN2 reaction the attack is from the back side. How this attack takes place from the back side? See, if we see this sigma bond, every sigma bond has its sigma star orbital. So we can represent this sigma star orbital like this way. Let's suppose I draw the hydrogen here. This for this red bond, the sigma star orbital would lie here. The MOT explains us this, that every sigma bond has its sigma star orbital. So when we take a nucleophile, it attacks into the sigma star orbital. It leaves two electron into the sigma star. So the sigma bond breaks. So we will form a transition state. This SN2 reaction proceeds via transition state where this bond is breaking, this bond is forming. The nucleophile and the carbon bond is forming and the second bond is breaking. Now, this is how the transition state looks like. Now, I want to ask you a simple question. Tell me, what would be the hybridization of the transition state? What will be the steric number you are going to consider? Whether it is a case of steric number 3 or whether it is a case of steric number 5 where you will be going with TVP geometry or you will be going with trigonal planar geometry. What do you think so? A straightforward question can be asked on this transition state also. What's your view on the transition state? It is very important because there are so many questions which are explained on the basis of its transition state. Yes, do share your views. Uh, Mosumi saying 3 SP2 SP3. Okay, trigonal planar, very good. 3 trigonal planar. Good morning, Kunal. Trigonal planar SP3. Okay, how it's possible? Okay, in SP3 you are considering it as the strict number 4. Okay, got your point. See, what's the reality is, when we see the transition state, the bonds which is breaking and which is forming has not been completely breaked and has not been completely formed. So we observe a kind of p orbital. We start to observe a kind of p orbital at this center and we start to observe a kind of p orbital at this center. Means we do not consider these bonds as to be the real bonds. in the transition state. So the steric number for this situation is considered to be 3. It means only we have 3 hydrogens attached here. And if 3 hydrogens are attached and a kind of p orbital is generating at the carbon center, then of course it is going to have a trigonal planar geometry. Trigonal planar geometry. It is very important to understand, yes, the transition state form here is have a trigonal planar geometry. And once the transition state completely breaks, the bond is completely break and the bond is completely formed, we form a product where a nucleophile is attached at the center and we have a 3 hydrogen attached here. Since the center which I have chosen is not a chiral center, so I will not be talking about the inversion here, but in further points we will discuss that also. So this is how the transition states look like. If I draw a potential energy diagram for this SN2 reaction, what does this potential energy diagram mean, sir? When I will try to represent this reaction on a graph. So on x-axis we have written as progress of reaction. We can also write, some books uses a reaction coordinate. What does this mean? On x-axis we are going to represent how the reaction is moving or how the reaction, what substituents it has involved, or we can say what are the key components of the reaction and what is its energy level, that will be represented on the x-axis, and the y-axis consists of energy. If you go up, the energy of the reactants are going to increase. So we have started from a reactant, let's suppose, whose energy lie here. In order to do any reaction, you need to provide some activation energy. So the bonds in the reactant are going to break and the energy of the reactant will increase and will reach a maximum, and then you will reach to the final product. The state of the reactant when its energy is highest, I repeat, the state of the reactant when its energy is highest is called as transition state. So in SN2 reaction, only one transition state is formed, and whose photo is like this. It is going to look like this, which we have drawn here. We have a reactant here, we have a product here. So this is what a transition state photo looks like. Now, if we see, we have only single step. If we want to write the rate expression, we got rate is directly proportional to concentration of substrate and the concentration of nucleophile also. Since we have only single step, in this step both of them are involved, so it will be directly proportional to substrate also and directly proportional to nucleophile also. If I remove the proportionality sign, we got a constant where a rate is first order with respect to a substrate and a first order with respect to a nucleophile. So overall, when I compare, I got to know that this is a second order reaction. This is a second order reaction. That's why we write SN2 as a bimolecular nucleophilic reaction, because it is a second order reaction. Got it? Sir, is transition state is activation energy of transition state? Sir, somewhere I studied that 50-50% of p orbital of Levin group nucleophiles takes place. See, spread pace. When we try to explain some other factors, let's suppose when I will be explaining you the rate in allylic substituents which goes via SN2 mechanism, then their pure p orbitals, or I can say that a p orbital formation is explained. Some books uses the formation of p orbital to explain this. So on that basis, we can say that it will be having a sp2 hybridization and a trigonal planar geometry. Okay. See, what I was trying to say is, I need to tell one thing. I forgot what I was thinking to tell you. Leave it. So we have a transition state whose energy lies somewhere here. Yes, the energy gap between the transition state and the reactant is your activation energy. This is the minimum energy which you need to supply in order to make this reaction happen. What is important in this page is, first of all, the transition state structure and its hybridization. This is important. The rate expression is important. Now, we can draw some conclusions on the basis of this. That's the reason we are not calling it sp3, because we have considered it as a p orbital. Okay. If we take choose it as a sp3, then we will have to consider, yes, Diksha is saying, then we will have to consider it as a steric number 4. It means then it will be becoming tetrahedral, no, which is not really the scenario. Okay, let's move ahead. Now we will be drawing some conclusions which will explain, uh, which will try to explain the SN2 reaction in more depth. For example, the first one will be the role of solvent. Which type of solvent do you prefer in a SN2 reaction? First of all, I want to know your point of view. If I talk about a role of solvent in a SN2 reaction, what are you going to prefer and why you are going to prefer? Chem Pacific is saying polar aprotic. Can you tell me the reason also why you will prefer a polar aprotic solvent and not, why not polar protic solvent? Your answers are absolutely right. Yes, sir. In a SN2 reaction, we always prefer polar aprotic solvent. There are a lot of examples for polar aprotic solvent like DMF, like acetone, correct? Like DMSO and etc. These all are different examples for polar aprotic. But what's the reason you prefer it? Because it stabilizes the transition state, increases the nucleophilicity. Very good. Polar aprotics, because nucleophilicity increases. Aprotic to increase the nuclear because it enhances the nuclear. Very good. Excellent. See, we have studied in, I think, lecture number 2 or 3 that how a solvent can affect the nucleophilicity. In a polar aprotic solvent, we always see the nucleophilicity is increased. It increases the nucleophilicity of a nucleophile. And in a SN2 reaction, that is what we want. We want that our nucleophile should be in high concentration, or the strength of nucleophile should be high, so that it would affect the rate of the reaction. See, we have directly proportional relation here. If the nucleophile strength will increase, the rate will also increase. So that's the reason we use polar protic solvent, because it increases the nucleophilicity. Can you tell me one reason why I cannot use polar protic solvent? Because it increases the nucleophilicity of anion, which enhances the rate of reaction. Can you tell me in the comments why I cannot use polar protic solvent here, which enhances the rate of SN2? See, whenever we will use polar protic solvent, it performs solvation and it will also solvate the nucleophile, and it is going to decrease the rate of the reaction. That's the reason we don't use polar protic solvents in a SN2 reaction. It means it is clear enough. In an SN1 reactions, since nucleophilicity does not affected the rate of reaction, it was not present in the rate equation. So it doesn't matter whether the nucleophilicity was decreasing. Hence we used polar protic solvents in the case of SN1 reaction. Polar protic solvent. Whereas in the case of SN2 reaction, the nucleophilicity matters. That's why we have used polar aprotic solvent. I hope you got the concept of the solvent, why we are using polar protic and aprotic. Okay. Yes. So this is the reason of using the particular solvents. Moving ahead, this was the point number 1, which will help us to understand a SN2 reaction. Uh, of course, we have covered this. We use polar aprotic solvent in a SN2 reaction. Now, always in a SN2 reaction, we form a inversion product as a final product. Let's suppose we have a carbon center which has a chiral center. Let's suppose we have here some sort of group, CS3 group. We have a hydrogen here. Below the plane hydrogen here, we have a deuterium, and at this center I have a X group. When the nucleophile approaches, it attacks in the sigma star orbital. We generally represent for any sigma bond the sigma star in this fashion, just behind the bond. So the nucleophile will attack into the sigma star orbital and the leaving group will be eliminated. If I skip the transition state and I draw the product directly, what I am going to observe is our nucleophile will be at this center. This complete product will be of inversion. If let's suppose I form this center is a chiral center, and if I find what is the configuration, then this will be taking the first priority, this will be taking the second priority, this will be taking third priority. So what will be the RS configuration? We will be having 1, 2 and 3. This is an anti-clockwise rotation, so it is S configuration molecule. And if I talk about, let's suppose my nucleophile was some which has the higher priority, for example it can be an oxygen center. So first priority to this, second priority to this, third priority to this. This is a clockwise rotation, and fourth priority below. So whenever an S configuration changes to an R configuration or an R configuration changes to an S configuration, we say that yes, inversion products has been formed. And SN2 reaction is famous for formation of inversion products only. These are the basic things which we have, which we know, but it's important to write down in our notes also. So this was point number 2, which told us that inversion products are formed in an SN2 reaction. Let's move ahead and see what we have more. Ring size. This is also one of the very important factor in an SN2 reaction. Recently, and in UPSC Geoscientist Prelims exam, a question was asked on the basis of ring size also. How ring size affects the SN2 reaction rate? Let's suppose I took an example where I have a 3-membered ring with a Br group. The second case is where I am having a 4-membered ring with a Br group. I have a 5-membered ring with a Br group, and at last I have a 6-membered ring with a Br group. Now I have asked you, if this goes via, let's suppose K1 rate, this goes via K2 rate, this via K3 rate, and this via K4 rate. All are undergoing an SN2 reaction. Can you tell me what will be the rate of SN2 here? Arrange them into the increasing or a decreasing order. Good morning, Komal. Yes, sir. Question आया geoscientist में. Yes, Preeti. Geoscientist prelims is generally they cover basic portion only, but they ask lot of question from reaction mechanism chapter. Try to answer what will be the rate order. A lot of questions coming 3 4 2 1 3 4 2 1 3 4 2 1. Very good. Yes, 5-membered ring exists in an envelope shape. 100% correct. See, when I compare a 3-membered ring and a 4-membered ring, we are dealing with a SN2 reaction. Okay. So the nucleophile wants to come and attack at this center and eliminate this PR. Whenever we compare SN2 reaction rates, the factor which works here is hindrance in deciding the rate of the reaction. For example, whenever we compare an SN1 reaction, the factor which works is stability or rate of formation of carbocation. Stability of carbocation or the rate at which the carbocation is formed. These are the two factors which governs the rate order for SN1, and for SN2 the governing factor is always the hindrance. So in the case of three-membered ring, there is a lot of crowding, there is no space in the bond angle is very small. Whereas when we move from a three-membered to four-membered ring, a bond angle has increased little bit, but now also this is very crowded in nature. But if I compare K1 and K2, we can say that yes, K2 has a little bit higher rate as compared to K1. If we expect that if the bond angle is increasing and the rate will be increasing, then we will be doing a slight mistake, because these two rings do not exist like this. A five-membered ring exists in an envelope shape, which is like this. This is that portion of envelope which you paste usually, and let's suppose we have a bromine attached here and a hydrogen attached here, correct? And a six-membered ring usually exists as a chair form, where a Br will prefer to be on an equatorial side, and we have hydrogens attached at this center. Now, in order to attack into the sigma star orbital, who for the five-membered envelope ring, the sigma star exists at this center, and for the Br, the sigma star orbital exists at this center. In a five-membered ring, the nucleophile can come and very easily attack into the sigma star and will eliminate the Br. Whereas in the case of six-membered ring, it is going to feel repulsion by the hydrogens which are present at the axial center. So when we compare the rate between K3 and K4, the rate of K3 will be higher as compared to K4. This completely happens because of the envelope shape of five-membered ring and chair shape of six-membered ring. So the overall order should be K3 will have the fastest rate, then K4, then comes your K2, and then comes your K1. This will be your order. I hope you got this concept. Yes, excellent. Because of envelope shape, the five-membered ring rate is going to be on a higher side. You can very easily compare this. Okay. Moving ahead, a small comparison between a SN1 and an SN2 reaction. We have covered few points related to SN2 reaction which were important. You can add one more point also, that SN2 reaction always proceeds via a transition state. So no rearranged products are formed in the case of SN2. This can also be one of the points. Now, it's very important to compare SN1 and SN2 reaction. Let's see, we will see point by point. You can note down these points. It will be better to revise if you want to revise your SN1 and SN2 in a one go. So SN2 is a one-step mechanism, we have seen that, and SN1 is a two-step mechanism. No problem. Sir, English course available from this channel. Yes, Anusha, you can contact our team for the English course and you can ask your queries. You can visit our website also. There you will get the contact number and you can contact our IFAS team. The SN2 is a bimolecular reaction, whereas SN1 is a unimolecular reaction. This we have already covered. SN2 is a second order reaction, it is a first order reaction. Product formation takes place via transition state. We have seen that yes, the transition state is sp2 trigonal planar, and for the SN1 reaction it is saying that the product formation takes place via a carbocation intermediate. Yes, we know that also. Point number 4, no carbocation rearrangement. Since no carbocations are formed here, so no rearranged product are going to be formed. But in the case of SN1 reaction, we always form a rearranged product. Point number 5, reaction is favored by polar aprotic solvent. We have covered that also. in a polar aprotic solvent nucleophilicity increases. That's the reason we use a polar aprotic solvent here. Reaction is favored by a polar protic solvent because it doesn't matter whether it is decreasing the nucleophilicity, it is increasing the nucleophilicity, but it stabilizes the carbocation. And in 90% cases of an SN1 reaction, these polar protic solvents act as a nucleophile. They only attack at the carbocationic center and we get our product. So this point also becomes important. Moving ahead, given mainly by methyl halides, they are saying that methyl halides generally go by a faster rate. They are mainly given by the tertiary alkyl halides. What they are trying to say is the fastest rate for an SN2 reaction is for your CS3X, a methyl halide. Of course, because hindrance is the governing factor and hindrance is very less in the case of methyl halide. So it will be giving the rate of SN2 reaction very fast. Whereas for an SN1 reaction, a tertiary alkyl halide will generate a 3-degree carbocation which will be very stable. That's the reason we are point number 6 is saying that it is mainly given by tertiary alkyl halide. If you look at the reactivity order, you will be having methyl halide 1 degree, 2 degree and 3 degree because of course hindrance, and here the order is as 3 degree, 2 degree and 1 degree, and because of course stability of carbocation. These are very few basic points. I will try to cover some more points from our standard reference book, that is Claydon also. They have given you a very fine chart also. I have not bring that chart today, but in the coming lectures I will be discussing that also, so that we are able to cover this SN1 and SN2 in a very holistic way from Claydon also. Okay. The mechanism is favored when the nucleophile is an anion. Generally in SN2 reaction we use a strong nucleophiles. In a SN2 reaction we prefer a strong nucleophiles. Why we prefer strong nucleophiles? Yes, because the nucleophilicity matters in the SN2 reaction, and if we compare, let's suppose, an anionic nucleophile and a neutral nucleophile, nucleophilicity of anionic nucleophile is more as compared to neutral. That's the reason we are preferring a nucleophile which is anionic in nature. Did you get the point number 8? This I didn't covered in the previous section, but this has been covered here also, here only. And if I talk about at the SN1 side, it says that the mechanism is favored when the nucleophile is neutral in nature. Of course, because of a lower nucleophilicity, as we are using solvents as a nucleophile. Point number 9 says that reaction velocity depends upon the concentration of the nucleophile. That is, mechanism is favored by high concentration of nucleophile. It is telling that rate is dependent upon the concentration of nucleophile. Higher the concentration, higher will be the rate of the reaction. And at the SN1 side, it is saying that reaction velocity is independent of the concentration of the nucleophile. With the term velocity, he is trying to explain you the rate is independent with the concentration of nucleophile. The last point says that inversion of configuration take place, and in the SN1 racemization take place. That's all what we have studied, and I have summarized all the points in one table only. If we have understood this, then we will try to solve some more questions on SN1 and SN2. Now there are few substrates which give which never give SN2 reaction, and there are few substrates which can never give an SN1 reaction. Where there are few substrates which give very fast SN1, and there are few substrates which gives very fast SN2. So we must be aware with them also. You can take screenshot of this if you want to write it down in your notes, or if you have written this, then it's very good. See, let's take an example of best substrate of an SN2 reaction. If we want to discuss a substrate, best substrate for SN2 reaction. See, whenever I have a CH3 C double bond O, CH2 and X group, a carbonyl whose alpha position has a living group is said to be a best substrate for an SN2 reaction. It gives a SN2 reaction with a very high rate. And if I talk about SN1 also, then alpha alkoxy groups, for example CH3, CH2, oxygen. Let's suppose I have CH2 in an X group. Such type of groups which have a oxygen group or any lone pair containing group adjacent to a carbon which is having the living group is a best substrate for a SN1, and this is a best substrate for a SN2. First of all, you need to remember these substrates. These are very important. Why this is best for alpha alkoxy 1? Why best for SN1? But because once the living group is eliminated, you generate a carbocation, and this carbocation is stabilized by the plus M effect of the oxygen atom. And the plus M effect is the strongest effect, I can say, in order to stabilize a carbocation, because it completes the octet of the carbocation. What does this mean, sir? See, if I draw the resonating structure, these will be the two resonating structures. And if I expand the hydrogen here, what we find is earlier the carbon which was having a carbocation was having 1, 2, 3, 4, 5 and 6. It means it was having in total 6 electron. It means its octet was not complete. But once the plus M effect has worked here, now we have 1, 2, 3, 4, 5, 6, 7, 8. Means each and every atom has a complete octet here. That's why a plus M effect is the strongest effect in order to stabilize a carbocation. If the carbocation is stabilized to such a higher extent, that's why this is called as the best substrate for an SN1 reaction. I hope you got this concept. Sometimes this becomes complicated, that how this is a best substrate for a SN2 reaction. See what happens. There are two ways to explain it. We can also explain this on the basis of MO theory, or we can MOT theory, or a simple approach can also explain why this is the best substrate. I will be going via simple approach. I will be not mixing here MOT in order to make it little bit complicated. Okay. Electron density withdrawn by CO group making less, sterically hindrance favoring backside attack of a nucleophile. Uh, See, if you are talking about electron withdrawing group, then withdrawing group or and hindrance are not working together. Okay, you need to understand this. What happens here is, see, let's suppose I have a nucleophile. Okay, now this center will also have a delta positive because halogen is attached here and it wants to go out. And of course, the carbonyl center has a delta negative and a delta positive at this center. When a nucleophile approaches towards the delta positive centers, this nucleophile is attracted by the carbonyl center also. Let's suppose we have a second scenario also, where we have CH3, CH2 and a X group. And a nucleophile is present here also, and in this case a simple alkyl halide is present. Now let's suppose if nucleophile is coming here with an x speed, I can say that x meter per second. Okay, let's imagine like this way. It is coming with a x meter per second. Then in the first scenario, since this carbonyl is also attracting the nucleophile towards itself, its speed is going to become twice. It means it will be approaching the center with a 2x speed. That's the reason in the case of first scenario, where the alpha position has a living group and alpha position to a carbonyl has a living group, will have the fastest rate. If I say here the rate is a K1 and it has a rate K2, of course K1 rate will be very high as compared to K2. So this is a very simple approach in order to understand why the rate in the first scenario is high. You will be surprised to know that if I place some CS3 groups, let's suppose I have a CS3 here and a halogen here, and let's suppose I have a CS3, one more CS3. Now in this scenario also, because of the effect of carbonyl, this also gives a SN2 reaction with a very good rate, and this all happens because of your carbonyl. This can also be explained on the basis of MOT. Actually, what happens, the carbonyl present whose pi star orbitals can involve with the p orbitals which are formed in the transition states. That's why the energy of the transition state decreases and the SN2 reaction rate is faster. I have given you little bit idea how MOT works, but you can understand this way also, that yes, carbonyl is helping to pull the nucleophile towards itself. Did you get this concept or not? Do tell me into the comments. Is it digestible for you? Sir, then there may be possibility to attack on the carbonyl rather than the CX. Yes, there is a possibility, but we are not looking at that aspect of the reaction. We are comparing the rates of a center when it attacks at the carbon center. Okay, that may be a possibility, but whenever you perform, let's suppose, mm, when you will be dealing with intermediates reaction, no, and if I give you a reaction of enolate alkylation, you form an enolate and you want to do an alkylation, form an alkylation product, and I give you this, an alpha alkoxy, not alpha alkoxy, living group which is at an alpha center of a carbonyl, then of course in that scenario you are not going to attack on the carbonyl center, you will perform an SN2 reaction. It means majority of the reaction move towards an SN2. Got it? So the rate of K1 will be very fast as compared to K2, the best substrate for SN2 and a best substrate for SN1. This is how they are going to look. Now there are few substrates which are not going to give SN2 ever, or not going to give you SN1 ever, or with a very extremely slow rate. So you must have heard about norboranes. If I draw a norborane, let's suppose, and we have a X group present at this center. Now, we all know that this is a bridgehead center and this is also a bridgehead center. Whenever we are going to perform a SN2 reaction, the nucleophile is going to attack in the backside of the of the living group, and it will be eliminated. We all know that during the transition state of SN2 reaction, the hybridization of transition state comes out to be sp2, and this is not digestible to the bridgehead center that its hybridization should become. Let's suppose I draw a nucleophile here and a dashed line with a living group here. This center cannot digest to become sp2 hybridized. That's why it is not possible to perform a SN2 reaction in the case of bridgehead carbons. And similarly for the SN1 also, if you want to perform an SN1 reaction, then you will be generating a pure carbocation here, and again this is not possible to form a carbocation in the bridgehead center. If it is possible, then also the rate is going to be extremely slow rate for the solvolysis reaction, or you can say for an SN1 reaction. So this is a substrate which will not give you either SN1 to SN1 reaction or either a SN2 reaction. There are few more points which Claydon books covers. There are few tables from the Claydon book. Today I have not bring that table, but in the next lecture I will try to bring that table portion also, and I will be covering that also. Okay, so that we cover this SN1 and SN2 in a very holistic way, and none of the point is left in for your SN1 and SN2 reaction. So I am keeping this much only for today's lecture, where we have covered about SN2 reaction. I hope you must have learned a few new things in today's lecture, and next week also I am continuing this series. I will be teaching you this substitution more, and I have planned 3 lectures for question and answer also. What we have studied till now, we will try to apply in questions. So that will be from, I think, Wednesday. And first 3 days next week we will be discussing about concept, and last 3 days we will be discussing about questions. Okay. Of course, we will have some questions, we will have some reference book discussion so that this topic is covered in a very holistic way. Okay. Thank you so much. Take care. Bye bye and happy learning.